Okay. Um, and um, so some things I may say might, if they apply to both my classes, I'll be sounding like a broken record to some of you, but just deal with it. Um, but I appreciate at least some of you having your cameras on. While I don't have any requirement about that, it's last semester for my undergrad classes, I just saw a sea of black squares and sore pictures, and it gets a little depressing. Um, so thanks to those of you who are doing that. Um, okay. Now, all right. And it's going to be checking periodically to see if those stragglers are here, but I guess there's not much hope there. Um, okay, so I don't really have much in a way of actual material to cover today. I never like to plan too much in the first day, so just kind of ease into it. So it may not really be a full class period, but I certainly need to take some time to talk about syllabus type things. Um, and it's also kind of weird. I think about half of you, or maybe a little more than half, have had me in class before, and then some of you are new to me. So this is going to be interesting. Okay, let me get the screen share going. Okay, so you should be seeing my canvas now. Um, okay, wait one sec. All right. Um, so this is where I have everything. Of course, you would have gone here to access this meeting. So I'm going to have the links to discussions for all class meetings posted here. The ones for current week will always be at the top, and then older ones below. Um, and then you can see all the assignments over here. So the homework problems have already been picked out for all 9 homework assignments. Excuse me. And then the also for the tests. Um, so we're still in, unfortunately, um, pandemic mode. Um, so that's why this class is online. The 2 tests that we see here, also have a final exam, will be of a take-home format. So something where I will um, post the handout for it um, on this site, and also my other class site that I'll show you in just a second. Um, and then you'll have a few days in which to do it, and then you would submit it um, to Canvas or by emailing it to me by the deadline. Of course, that means because it's take home, the problems would be somewhat more involved than for a. Um, oh, okay. um, uh, I'm glad someone's happy about that. So, um, will be somewhat more involved in what would be on an in-class test, which is what I had the last time I taught this class. Okay, so but you'll be able to see all your grades up to the minute here. Also, any feedback on assignments will be posted in Canvas also. So whenever I grade an assignment, um, I'll add as a comment in the Canvas gradebook. Okay, here's where you lost points and why. Okay. Um, Now, I actually have 2 class websites. So I've been doing everything in Canvas since we were required to because of COVID. But if you go to my, hold on, let me check things in Canvas, make sure I'm not missing anything. Okay. Um, if you go to my main web page that we see here, so www.math.usm.edu/Lambers, and on courses, click on courses, you have everything that I've ever taught. So you might find things for other classes that you'd be interested in. And the last time I taught 417 was quite a while ago in spring of 2014. Um, so um, But so now we have this side here, so I'll show you. Okay. So this is the kind of class site I've been using for years. I wanted to continue doing that, especially if for those of you who would prefer not to use Canvas. So we have a copy of a syllabus. So all the information that is in the official syllabus posted on Canvas is replicated here. And here's a breakdown for your grade. Notice of 9 homework assignments, the lowest 2 will get dropped. Now, the assignments, you have a full list of problems. This is also on Canvas, and the due dates are all here. Everything is been laid out. So unless there's something like a natural disaster, we are due for a nasty tornado. It seems to happen every 4 years. This is a schedule that I will follow. Now, those of you who have had me in class before know that I'm not really a pain about homework deadlines, but so they're more advisory. But keep in mind that you do need to know these things for tests, so I'd recommend getting homework done for that reason, and also not necessarily just not doing the last 2, because that material will show up on the final exam. Okay. Now the textbook, Partial Differential Equations for Scientists and Engineers by Farlow. That is, so this is a book here, or at least the cover may look different. This is the Dover version. So I'll be pulling the problems from there. Now, one thing I want to point out is a lot of the problems do have answers in the back. I've found in some cases those answers may be wrong. So that's something to be careful about. Okay. On the resources page, I have my notes. These are notes from when I taught the class last time. So if I go ahead and open that up, I've basically taken all of those notes and assembled them into a book. It's not a very long book; it's 60 pages long. But these correspond to all the all my lecture notes that go with the different lessons. So I will be basing my lectures on these notes. So in fact, you see this first one, that's for today, is edited and reproduced here, but during class, like for instance, based on questions, or if I feel like something needs elaboration, I will add to this, and then post this in Canvas and on the site I've just been showing you. So this will be more up to date, but at least you have a starting point for what I'm going to cover right here. So that's on the resources page. Okay, I want to point something out about the schedule for this week here, the second week of March. Now, because of a pandemic, the university is going with a modified academic calendar in which the spring semester ends earlier than usual, so finals are wrapped up by April 30th instead of spilling into May. And therefore, there's no Mardi Gras break, there is no spring break. And while I understand that reasoning, my thinking is that by the time we get to this point in the semester, several weeks in, chances are you will need a break. You will not need a break any less just because the semester is going to end sooner. It's not really all that much sooner either, maybe 1 week. And I will feel like I need a break too. So while I'm obligated to hold a class meeting on these days, unofficially, from your point of view at least, this is your a spring break from this class. so I will not have anything due. I will not be covering new material. If you want to, I will be here in Teams. If you want to appear to ask questions about any ongoing homework, like for instance, maybe you're struggling with this homework 5 that's going to be coming up then, certainly you can do that. Or you can just say, you know what, at least for this class, you're on spring break. And I'm doing this in my other class too, in Math 610. So nothing else you can lighten your load a little bit. Okay. Okay. But then no one else will be doing it, so you'll just have to keep your other activities going, unfortunately. But hopefully this helps you out a little bit. Okay. All right. Now, before I get into any material that I have lined up for today, does anyone have any questions about the course and how it will be run? Let's see, we have, which update my attendance. Oh, I'll do that later. Okay. Okay, let's check the chat. Wait. Oh, okay. Okay. The difference with, for 417 versus 517 students, that there will be something somewhat extra to do on the tests. So for example, if I assign 6 problems for 417, maybe 7 problems for 517. So there would be a little extra work in that. So that's the extent of it. Okay. Walker, do you have a question?
Yeah, so that book you showed us earlier, is that just a link to see the book, or is it an actual PDF of the book?
It is an actual PDF of a book. So,
sweet. Okay, just making sure. So we don't need to buy it.
That's right. And as someone who makes a little money off a textbook I've written, I feel bad about throwing this author under the bus, but yes, this PDF has been out there. So hopefully if anyone has bought the book, that either they can return it or they're fine with having it. But if you would like the PDF, I'm happy to make that available to you. Or I can post it in Canvas. Okay. Yeah, but everything is here. It's not a great quality copy, I must say, but it'll work. Okay. Other questions? I see we have some feline company. always welcome. As you can see on the side, I have my own cats page. Although, unfortunately, both of them have gone on to a better place. These are old pictures. But I, as of this past Christmas break, I do have a dog, a new dog. So I will be adding that to this site too as soon as I get a hold of some pictures of her. So. Oh. His name. They are our best mental health therapy for getting through this pandemic. Okay. Oh. Yes, Taylor. Yes, from our meetings, I remember seeing your cats and laying all over the place. Um, okay. Any other course questions? Okay. All right. So, like I said, a lot of you know me from prior classes. So, for those of you who don't, uh, uh, I'm Jim Lambers. Of course, everybody calls me Dr. Lambers because we're all nice and formal here in the South. But um, uh, so this is my 11th year as a faculty member at USM. So I'm a full professor and director of a graduate program, um, and I got my PhD at Stanford University after doing my undergrad at a different black and gold school, Purdue. So I got my PhD in 2003 in scientific computing and computational mathematics. Um, and my specialty really is an intersection of a couple classes in our undergrad curriculum. One of them is this one, partial differential equations, but I focus on numerical methods for solving such equations, such as those that are taught in Math 460 and 461, which that sequence I'll actually be teaching next year, or 560, 561 for graduate students. But in this class, we deal with analytical methods for solving partial differential equations, or PDEs. So oddly enough, and we actually don't have a undergraduate class that deals with numerical methods for PDEs, but we do have it at the graduate level. But as an undergrad, you get to learn about like I said, analytical methods for PDEs from this class, and also numerical methods for ordinary differential equations, or ODEs, for instance, taught in 461. And then all that is merged together, and you get to see what I do for publications and such. Um, but partial differential equations are extremely important for applied mathematics. In fact, I wouldn't even dream of getting into applied mathematics without learning about them. So, so this is a very good course to get a feel for what applied mathematics is about. And I believe that we have some physics majors here. I believe are required to take this class. Is that still true? But they're required to take it. Um, and
Yeah, I'm a physics major, and I think two other people in this course are too, and yeah, we're required.
Okay. Yeah. So that maybe the reason we continue offering this class every spring, because math majors aren't required to take it, but physics majors are. So it's kind of strange. Um, so, but it's good to have a whole lot of you here. I think there are uh, 18 of you or something like that. Okay. Although looks like still only 17 of you are here. Okay. So. Um, So here we'll just give a gradual, gentle introduction. Okay. Um, so, so first of all, what is a partial differential equation? Um, so there are equations in which the solution is some function, which I'll often use the letter u to refer to the solution of a PDE. Um, and what makes it a PDE is that the equation involves partial derivatives of this solution with respect to whatever variables you may have. So generally, such variables are correspond to space and time. So we'll be seeing equations that depend on partial derivatives of your solution u with respect to x, y, or z, or t for time. Okay. Um, okay. Now, you may already be familiar with ordinary differential equations. Now, ordinary differential equations, the solution depends on only one variable. So, for instance, in Math 285, those of you who've taken that, which is a prerequisite for this class, the solution may be a function of only x or only t. Just as you make a transition from single variable calculus, like Cal 1 and Cal 2, to multivariable calculus, which is our Cal 4 or Math 280, and dealing with partial derivatives of functions with respect to x, y, or z, or t, here we're making the jump from single variable to multivariable in terms of our differential equations. Throughout this class, I'll be using this notation of referring to partial derivatives using a subscript. So u sub x is the same as the partial derivative of u with respect to x, because we'll be having partial derivatives all over the place. So we definitely want to use the most concise notation possible. So you would have seen this notation in multivariable calculus. So it's important to keep that in mind. Like from now, for literally from this moment, as I use this notation. Okay, and some techniques for solving ODEs will be helpful to us in solving PDEs. Okay. All right. Now, I'm going to give a few examples of PDEs. In fact, these are the main PDEs that we'll be studying this semester. The heat equation, Laplace's equation, and the wave equation. And it's going to be an opportunity for me to introduce additional notation. So the heat equation is where a partial derivative of u with respect to t for time is equal to this expression that I've defined down here. So this is called the Laplacian of u. So the Laplacian of u, as we actually see this involved in all three of the primary PDEs that we'll be studying, it's a sum of all the second partial derivatives of u that are with respect to the same variable in both cases. So uxx plus uyy plus uzz if it's 3 dimensions. If it's 2 dimensions, then we would just have uxx plus uyy because there's no dependence on z. Now, these are not all the second partial derivatives. We also have, for instance, uxy or uyz, but those are not included in the Laplacian. We're only summing up the ones that are with respect to the same variable for both differentiations. Okay. And this is what the Laplacian looks like in Cartesian coordinates, the customary coordinates of x, y, and z. But now and then we'll need to use other coordinate systems that you would have seen in multivariable calculus, such as polar coordinates. So this is what the Laplacian looks like in the polar coordinates r and theta. So that changes the partial derivatives that we have, and we also have these coefficients of 1 over r and 1 over r squared. Sometime later, I will show how this is derived from this definition here from Cartesian coordinates. Okay. Now, so the heat equation is du dt is equal to Laplacian. Laplace's equation is just the Laplacian of u is equal to 0. And then here we have the wave equation is second derivative of u with respect to t. So utt is equal to Laplacian. These are the simplest forms of these equations. What we'll see for the heat equation, we have a constant coefficient here or here for the wave equation, but that can always be removed by a change of variable to make that coefficient equal to 1. So these are the simplest forms of these three PDEs. We're going to spend the first part of a semester looking at the heat equation. Then we spend some time on the wave equation and also some other first order and also nonlinear PDEs of a similar type. And then we will end the semester by looking at Laplace's equation. Okay. All right. Now, I want to mention so Laplacian have used this notation delta U. Okay. But it can also be written this way. Now, can anyone tell me this symbol? What does this symbol normally refer to in calculus?
Gradient.
Yes, that's used to refer to the gradient. So you might think it's like, oh, you're taking a gradient twice, but that doesn't actually make any sense. Just based on the definition of a gradient, because the gradient of a function u is a vector quantity consisting of ux, and uy, and uz, all the first partial derivatives. But the reason why it's written this way is from this, that the Laplacian is actually equal to this expression here. Now, let's see how well you all remember your multivariable calculus. So this is the gradient of u. So this is a vector consisting of ux, uy, and uz if you're in 3 dimensions. But here, this takes on this upside down delta, this triangle takes on a different meaning in this case. Can anyone tell me what this operation is? It's not gradient. What operation is that when you include the dot here?
Is it a dot product?
There is a dot product involved in the definition, but what I'm asking for is the name of this operation that's being applied to the gradient. Well, I'll see if anyone knows that. I'm going to type out what this means in terms of a dot product. Because you can think of, so this triangle in both cases is referred to as a del. So you can use del dot gradient. Oh, that's actually not the name I'm looking for. But what we see happening here is the dot product of this vector of differential operators, partial respect to x, respect to y, and then z, dot product with vector of its gradient is ux, uy, uz. Now, what is a dot product? A dot product is when you multiply corresponding elements together and then add them up. Well, really what's happening here is we're applying the ddx operator to ux, so that gives us uxx, and then here we have ddy of uy is uyy, and then ddz applied to uz is uzz, and then we add them all up, and that gives us uxx plus uyy plus uzz. So no one remembers what this operation is? You would have seen it in multivariable calculus. Divergence. This is the divergence of gradient. So it could be written this way. Divergence of gradient of u. Oops. All right. So here we see two of the three main operations from vector calculus, the divergence, the gradient, and what's the other one?
The curl?
Yes, the curl. So in fact, one of the best known textbooks for vector calculus is literally titled Div, Grad, Curl, and all that. So what's interesting is what's known about these operations is the curl of any gradient is 0. The divergence of any curl is 0. And some of the combinations of these operations actually wouldn't make sense, but this one does. Divergence of a gradient is not 0, it's the Laplacian. Okay. All right, so this notation for the Laplacian is very common. I think I've seen this almost as frequently as this. So I wanted you to be aware of both, but I also wanted to explain what this notation means. Okay. And also give what's apparently a necessary vector calculus refresher. Okay. So for these PDEs, the independent variables are t for time in the case of a heat equation or wave equation, and then whatever spatial variables you may have, x, y, possibly also z if you're in 3 dimensions. So those are the independent variables, and u, the solution, is the dependent variable. Just to put front and center all the terminology that we need. Questions up to this point? Okay. Why do we bother with PDEs? What we'll see is that PDEs are derived, certainly the ones that we have just seen, from natural laws. For instance, conservation of mass or conservation of energy. I'll be using a balance like that, conservation of energy, next week to derive the heat equation. So based on balancing of heat energy. So once you derive a PDE from various physical laws, then solving that PDE can help you understand the behavior of certain quantities. So, for example, actually, I should go back to this and elaborate. Sorry, I meant to do this earlier. What does U mean? What does solution mean in these cases? So here U so U is a temperature throughout an object. So the domain of the PDE would be the object that you're modeling the temperature of. Okay. Hold on a second. The one student who's not here is needing help. Navigating to this meeting. Okay. All right. So that's what's being modeled in this case is the temperature. So the object is the domain of a PDE. And so what this allows us to do is get an idea as to how the temperature in the object is going to change over time or within the object. Okay, so that's the heat equation. Laplace's equation is for modeling electrostatic potential. Laplace's equation can also come up from, let's see. Sorry, I almost misspoke there, but like here we have Laplacian of u is equal to 0. Laplacian is equal to a constant times u is an eigenvalue problem, and that will help us with solving some of these time-dependent PDEs here. Okay, so that's what's being modeled in this case as a function of spatial variables only. Okay, the wave equation, its interpretation depends on various things, but I'll give you one interpretation that we use for purpose of deriving the wave equation later. Okay. In one specialized to one dimension. So in one dimension, the Laplacian simplifies to just second derivative with respect to x. It can usually model the displacement of a vibrating string. So you would be the at any point in space and time is the distance of that portion of the string from equilibrium. So I'll show how this form of wave equations is derived when we get to that part, but that's going to be some time from now. Okay, but there are all other kinds of vibrations that can be modeled using wave equations. So at that time I'll be discussing those too. So here we have the diffusion diffusion processes can model using equations such as the heat equation or variations of it. Here we have a wave equation modeling any kind of a propagation of sound waves, water waves, etc. And then we have electrostatic potential in this case of a Laplace's equation. So here are the kind of things that can be modeled using PDEs. But that's just a very small subset. To give you an example of how these equations can be used for very different problems, I actually use an equation like the heat equation for image processing. So if you think of an image, let's say a grayscale image, or a color image separated into components like red, green, and blue components, the image is defined in terms of pixel values that range from 0 to 255. So 0 for black and 255 for full color saturation. If you want to remove noise or fuzziness from the image, so you want to have sections of the image that have small fluctuations in color to be smoothed out. That is, you're modeling a diffusion process. Okay, let me write some of this down for the notes. Okay. Because what happens to heat energy over time? It diffuses. Like if you have a heat source in a room, over time, the temperature throughout the room will converge to some kind of average. So an ambient temperature. And that's what we want in that kind of smoothing to an equilibrium is what we want for removing noise or fuzziness from an image. So if we think of the original fuzzy image as the initial condition, and then we apply an equation like the heat equation to it, then we have smoothing going on, which enhances the image. So any process that is diffusive in nature can be modeled using equations such as this one. This is the simplest form of it, but equations like this have this fundamental behavior. Are all kinds of propagation problems that could be modeled using equations such as a wave equation. So there's quite a few possibilities here. So I mentioned this because this is one of my aspects of my my research program. Okay. That's why all the different partial derivatives that you see in the equation, you can refer to a variety of things such as velocity or acceleration or flux. And as we visit the individual equations and study in more detail, I'll let you know what are interpretations of physical interpretations of the derivatives that that we see. PDEs give us a way to understand the effect of physical laws on objects. So, for example, by modeling a temperature over time, we can see how the temperature is going to change over time, so we can gain some insight into underlying physical processes from a solution of a PDE that we obtain. So how do we solve PDEs? There are quite a few methods out there, some of which we'll see in this class. If we can separate a PDE into multiple ODEs, like one for each independent variable that we have, then we can leverage everything we know about solving ODEs to solve the original PDE. So we'll certainly be working this one a lot. In some cases, integral transforms, such as a Fourier transform or Laplace transform, and there are many other transforms out there. We'll be focusing on the Fourier transform in this class. Can be used to transform a ODE into an algebraic equation. So if we can take a PDE that say has two variables, say space and time, so by applying a Fourier transform, which is applied to the spatial variable, then what we are left with is an ODE in only time. And we'll actually see this several lessons down the road. Okay. Eigenfunction expansions are actually related to integral transforms. Excuse me. If we can express a solution in terms of certain basis functions, such as sines and cosines or exponentials, then the only unknown in the solution are the coefficients in this linear combination. So then we can solve ODEs to obtain these coefficients. And then, not a focus of this class, but as I mentioned before, this is a focus of my research, numerical methods in order to find approximate solutions, because a lot of PDEs cannot be solved analytically. So the PDEs we'll see in this course, we'll be able to write down formulas for a solution in many cases. But that's for the simplest form where you assume like coefficients are constant and things like that. But then you have more complicated forms of these equations, for example, of coefficients that depend on space or time, where such analytical solution is not possible. Then you rely on numerical methods. But understanding a solution from these simpler cases can help with the design of numerical methods. Okay, there are many ways of classifying PDEs. So I want to discuss how we can the different ways of classifying them, because that will focus our study of them. So what is the order of a PDE? So we look at the highest order derivative. Now, the PDEs that I showed you earlier, heat equation, wave equation, Laplace equation, those have either first or second partial derivatives. So all of those are second order. But for example, the beam equation from Euler-Bernoulli beam theory has a fourth derivative with respect to x in it. So that is an example of a fourth order PDE. Yeah, how many variables? Independent variables. So for example, if we're in 3D, then the heat equation or wave equation has 4 independent variables, x, y, z for space, and then t for time. Linearity. I admit when I wrote these notes 7 years ago, I was being a little lazy. This is a bit of an oversimplification. That does not always apply. Okay, if the PDE is homogeneous, in other words, if it can be if 0 is a solution of a PDE, then this applies. That a linear combination of solutions is also a solution. So as an example, the 3 PDEs I've shown you, heat equation, wave equation, Laplace equation, because as I've written them, there are no source terms. They're also linear equations. So in other words, if I have 2 solutions of Laplace's equation, so Laplacian of U1 is 0, Laplacian of U2 is 0, and the Laplacian of any linear combination of U1 and U2, for instance, U1 plus U2, Laplacian of that sum will also be 0 as a result of this equation being linear. But if I had, for instance, Laplacian of U is equal to f for some non-zero function f, then 2 solutions of that equation added together would not be a solution of the original because of that source term f. Because that equation is not homogeneous. But all 3 of these PDEs are linear PDEs. Okay, now if you have any coefficients in linear PDEs, whatever coefficients you have are allowed to depend on independent variables, but the dependent variables coefficients cannot depend on them. So I want to give you a contrast here. For example, a variable coefficient heat equation, that is an example of that is also a linear equation. Nonlinear equation Okay. I just want to check something here. Oh. Okay, so now we have full attendance. Good. Okay. Sorry, I need to correct this. It's named after burgers, not burger. So Burger's equation is an example of a nonlinear equation because of this u right here. So you can think of a coefficient of du dx as being u, and because the coefficient depends on the solution, it's not a linear equation. So that's one thing to keep in mind. I could be a little more specific. This equation is called quasi-linear. Now it has the appearance of a linear equation, just that the coefficients depend on u, of a dependent variable instead of just the independent variables. So I'll give you another example. Where here we have a nonlinear function of a derivative itself being taken. So so here this goes one step beyond quasi-linear, and we call it fully nonlinear. Okay. This equation I just made up just to illustrate the terminology. Okay. An equation like this, Burger's equation, is an example of a equation that comes from conservation laws, which we'll see much later in the semester, including an equation for modeling traffic flow. So yes, traffic flow is something that can be modeled using a nonlinear PDE. And that can explain some of the phenomenon you see in the behavior of traffic. So as an example, we wouldn't get an example like this here in a smaller city like Hattiesburg, but for example, say if you're out in LA where there's orders of magnitude more traffic, suppose, but you may also observe this in other cities such as like New Orleans, closer to us, like New Orleans or Houston. In fact, I did experience this in Houston recently. That if you are driving along the interstate and there's a fair amount of traffic, it's fairly congested, and but everyone's moving along pretty well, and all of a sudden you slow to a crawl, and there's no identifiable reason why. Like there's not an accident, no, nothing like that, but everybody just slows down for a bit, and then slowly but surely starts moving again. So and it's frustrating because you wonder why is that happening, and that's something that actually can be explained mathematically through a behavior of a solution of a PDE for modeling traffic flow. So I'll talk about that later when we get to that point. But it's kind of cool to see the math in action in real life as I have. Okay. Okay, this is what I mentioned earlier about homogeneous. So if 0 is a solution of a PDE, which applies to all the equations I've shown you, like heat, wave, and Laplace equation, then we say the PDE is homogeneous. Okay. So often we learn how to solve the homogeneous version of a PDE first, and then we add in something here, like something non-zero on the right side, and then we figure out how to solve that. Okay. Coefficients can be constant coefficient or variable coefficients. So the PDEs we've seen so far all have constant coefficients. Here's an example of a variable coefficient that depends on x, or also depends on u. So all three of these here, these examples, are variable coefficient problems. If you have a PDE that depends on two variables, it could be x and y, or it could be like x and t, where y plays a role of t here. Then if you can fit it to this form, a second order linear equation. So actually this is the most general second order linear equation in two independent variables for coefficients a, b, c, d, e, f, and then source term g. So, and we're not assuming that these coefficients are constant either. So we can classify these PDEs as, whoops, need to fix my notes here. Okay, as parabolic, hyperbolic, or elliptic, according to the sign of b squared minus 4ac, the familiar discriminant from the quadratic formula. So for whatever coefficients a, b, and c that you have, so d, e, f, and g are irrelevant here. If it's equal to 0, it's parabolic. If it's positive, it's hyperbolic. And if it's negative, then it's elliptic. Now, that does not mean that the equation or solution relates in any way to these conic sections. These are just the names we give according to these situations. Now, whether the equation is parabolic, hyperbolic, or elliptic fundamentally affects the behavior of the solution. And this is why we study in an introductory PDE course heat equation, wave equation, Laplacian equation, because these equations are of a three different types. So it's because for general conic section, like if we think of, instead of uxx, we have x squared, and then we have xy, and then y squared. If we have a conic equation like this, and b squared minus 4ac is equal to 0, that's the equation of a parabola. And similar classification for a general equation of a hyperbola or an ellipse. So that's where we get these names. But the sign of its quantity affects what kind of behavior we get of the solution. And later I'll talk about characteristic curves to elaborate on the differences between these three types of equations. Excuse me. So at least in this course, you get exposure to all three kinds. And what we'll also learn about is if you have an equation of this form, and let's suppose that you determine that it is parabolic. Well, it would be nice to be able to transform this equation into a very simple form of the heat equation that we see here to be able to solve it. So it turns out it is possible to transform that kind of a general second order equation, this one, into one of those, into some kind of canonical form, one for the parabolic, one for hyperbolic, one for the elliptic case. So once you classify it, then we can transform it, and that puts you in the path to solving it. Now, I should mention, though, equations can change types. Now, since I'm not assuming that these coefficients, a through f, are constant, if they are functions of x and y, then it's possible for a PDE to change types. So for some portion of your domain, the equation may be parabolic, and elsewhere it may be hyperbolic. And that's quite a headache for solving it, whether analytically or numerically. And there are some problems out there that change types within the domain. So we're not going to get into that in this class, but I want to make you aware about some of the particularly nasty problems that researchers have to deal with involving PDEs. So whenever we come across a PDE, you want to be able to classify it, understand what is its order, is it linear or not, is it homogeneous or not, and if it falls into this category, is it parabolic, hyperbolic, or elliptic? As a first step towards solving it and understanding the behavior of a solution. Okay, so this is our start and about PDEs in general. And so then on Monday, I will get started on the heat equation and how we can go about deriving it and also, of course, solving it. Are there any questions about anything I've covered here?
I do have a question. Are we going to have access to the notes that you were filling out with all the different side notes you added?
Yeah. So whatever I do in class, whatever editing I do, I will post this in Canvas later. And since I'm recording this, I will also post the video. So I from all these classes, I now have quite a YouTube channel going. I never watch it. I hate to watch myself teach. But okay. Other questions? Well, I know everybody's like, "Hey, I want to get out of here." So, okay. Yeah. So each class day by sometime in the evening, because I have to do this for 2 classes that some of you have just endured. I'll try to get all this in Canvas. And what's the videos, like when I save this recording, it'll go to Microsoft Stream, but apparently some students have trouble accessing that, so then I just also put it in YouTube. And I'll have a Math 417 playlist that has all the videos there, because who wouldn't want to binge watch this? Okay, so all right. Let's see. I don't think I have any assignment from. Oh, okay. Yeah, there are a few very simple problems from this lesson, so you can at least get started on that portion of the homework. But there's a good chance that with a hour and 15-minute class period that I'll try to leave some time at the end for any homework questions. But I do my best to answer emails quickly if you have want to send any questions that way. And as far as let's see, I think I have it up here. Oh, no, I don't. Oh, wait, someone's hand up. Oh, Haley?
Yeah, I just wanted to make sure you said you would be able to post the PDF of the textbook on Canvas for us.
Yes, I will post that too.
Okay, thank you.
Okay. All right. What do you see in front of me is my schedule. I have a lot of students that I meet with. So that's in yellow. So some of you are seeing yourselves there. And so we do have some gaps. So for instance, when I would be available easily for an office hour would be like after 4 o'clock on Tuesday and Thursday. Also, I have this gap from so I have meetings at 9:15 and 11:15. So from 10:15 to 11:15, I'd just be sitting around waiting for my next meeting. So you can hit me up for questions then too. But that's just for office hours. And then if neither of those work, we can figure something out to arrange a time. So because now and then I get cancellations or I have other gaps in my schedule. Okay, but I'll post something about this in Canvas also. Okay, so I guess I have a number of things to remember to post in Canvas. So if you check like by tomorrow, for instance, and don't see it there, then definitely let me know. Okay, are there any remaining questions? Okay, then I guess you're free to scram now. And I'll stop the recording at this point. Yep. Oh, let's see.